We are really going to talk about those standard deviations. Okay? We're going to talk about those standard deviations that we kind of started yesterday. We're going to get those percentages down for how much it counts for underneath the curve, and hopefully by the end of today, you're going to understand a lot more about a bell curve. So here's what happens with a bell curve. All right, so let's investigate what the standard deviation can tell us about a normal distribution. Again, remember, this is very important that it is a normal distribution, okay? So the relative frequency of the histogram for the battery lives of e-phones and unlimited cell phones are shown. The normal curves are mapped on the histogram. You see this negative 1s. What did we say S stood for? You're in trouble. Yesterday, you should have learned that it stands for the standard deviation of what? Of a sample, because are there more than one standard deviations? One is a standard deviation of the population, which means you counted everyone and everything, and one is the sample, which means you didn't do the whole population, you just do the piece of it. Okay? So there's definitely a difference. That S stands for a standard deviation. So this is, does everybody see, this is the mean. That's where they added up all the phone lives and divided by how many phones there were, and they got 10 was the mean average. You follow me? Then what they did is they found this thing. We're going to teach you later on how to find the standard deviation. They found the standard deviation, and this is called one standard deviation, and it's below. And this is one standard deviation, and it's above. Does everybody kind of understand that? Notice, what do you see about the standard deviations? It's from 10 to 9.5, yes? This standard deviation is to 10.5, yes? Watch what happens when we go down here. We have this right here, which is 10. One standard deviation is 9.5. One standard deviation is 10.5. Here's what that means. Right here. So when they do this data, this is not the actual, this is not the normal distribution, but they're trying to show you that this is actual data. When you calculate this, 33% of the phones fall between this and this. And you can look back at your chart and see that. 34% of the phones fall between this amount of time. Now, that is not the actual, like that is not the normal one. This is just the actual data. But it's really, really close to the normal one. Here's the one, this is the rules that we want to get to. This right here. The ones that were up there were just based on the phone. That's not the one that we really need to concern ourselves with. They're just showing you, if you counted it up and you did that, that's what's going to happen. This is the one you need to know. Okay? Approximately 68% of the data in a normal distribution for a population is within one standard deviation of the mean. So what that means is, if I have, so these are my cell phones, okay? This is 10 hours, it's right here. That should be right there. That's the mean. That's when I add them all up, the average mean is 10. Well, when I do the rest of the data, one standard deviation below and one standard deviation above, that should account for 68% of all of my phones. All of my phones, 68% of them should fall between 9.5 hours and 10.5 hours. Does that make sense? Now, that means that my standard deviation is 0.5. One time I add 0.5, one time I subtract 0.5. Does that make sense? Now, if I go out another standard deviation, so now I go out to here. How much, what do you think is going to happen? Now we're going to gain this many more phones and this many percent of phones, right? So what do you think my percent is going to do? And the rest of this, see, we're talking about the area underneath it. Is there much left over? No. Because guess what? Out here, 3 standard deviations, there should hardly be any phones that are out there. Maybe 1 or 2% of the phones should fall. Probably even less than that. And we're going to get to that in just a minute. Are you kind of understanding? Right here, when you go over, watch how many percent should fall within 2. 95% of the phones should fall. So what does that mean for me? If I go over 1 standard deviation, we'll pretend this is 10 for our phone one. Remember, the phone one didn't fall perfectly, but it was darn close. What does that mean this one? 1 standard deviation was 9.5, yes? What does that mean over here? Just be 9. Because how much do I subtract every time I go over a standard deviation? 0.5. When I go over 1 standard deviation, it's going to be 10.5. When I go over another one, it's going to be 11. So, if I asked you, I said, I want you to be pretty confident. What amount of time do you think your battery is going to last if you ordered it from this cell phone company? What do you think it's going to be between? And you're almost 100% confident this is how much battery life. So you're working there, you're going to say your battery will last between what? 9 hours and, because I'm 97% sure that that's what's going to happen. 97% of my phones will last from 9 hours to 11 hours. Does that make sense? Now, do you notice how this was all of this was 68%? Isn't this the same distance as this? Isn't this the same area as this? So what do you think if I just went this from here to here? What do you think percentage of the phones fall within below 1 standard deviation? Just 1 standard deviation below, not and above, just one below. What do you think this percentage is? And what do you think this is then? Does that make sense? Right? Well, if this accounts for all of this, accounts for, I know we're getting a lot, all of that accounts for 97, we said, correct? Or 95, correct? How much do we already know this accounts for?
68.
68. So what can we do with the 95 now? Minus. And then what do we have to do after that? So this is going to be 8, right? This is what? 7, 27. What do we have to do with that, you think? Divide it by 2 to get how much this percent and this percent. So you realize that this percent and this percent is 27% of the, right? So if I divide it by 2, you guys following me? Now, when we go over 3 standard deviations, now how much of the data is included? 99.7%. Because is there a possibility of crazy outliers with almost any data set that we get? Yes. How much will those crazy, way, way far outliers, how much will they account for? 0.3%. We're talking very few that are really crazy outliers. 97%, 99.7% of my data should fall within 3 standard deviations of the mean. So let's see if you understand what I'm talking about. Test scores, because they use, by the way, this is how a lot of, your standardized tests, a lot of them, this is how they used to grade them. They're saying they're getting away from it, but I don't know if they truly are. But this is how they used to grade all the tests. And you tell me why I think I believe that this is a very terrible way of grading tests, personally. What do you have to have in order to grade, in order to make a bell curve? What do you have to first have? A mean, right? So they take everybody's test score, they add them all together, and then divide by how many students took the test. Does that make sense? Well, from some of the stuff that I saw, the tests were so hard that everyone was bombing them. So you could have, we'll make it more real for this one, and then we'll talk about what can happen after. So they'll say, let's say that it's a 65% was my mean score. You following me? And the normal standard deviation is 5%. You with me? What does that mean? What percentage would be my standard deviation below? 60. What would be my standard deviation for above? And what does that mean for me? Now we're going percent, because it's a test score, so if you have a question, please make sure you ask. I know that 68% of my students scored between a 60 and a 70% on my test. If it is a normally distributed bell curve, that's what should happen. Are you following me? 68% of my students should either score a 60 or a 70%. Going out a little bit farther, going out another standard deviation, what will this be? 55% and what do I now know? That 95% of my students scored between a 55 and a 75. You with me? Now, why do I personally think that this is a terrible way to grade tests? What if my mean is a 40%? See, what has to happen is, the way they do that is, this is like, if this is the mean, that means 68% of my students fell within this region, right? Well, if it's a state test, do they want to fail everyone? So, basically what was happening is, all you were doing with the bell curve is you were comparing everyone to everyone else. Well, and I'm not trying to be mean, what if every student is really, really dumb that year? All you've done is you compared them to themselves. And again, I'm not trying to be mean. I don't want to compare myself to someone who's not very smart. I want to make myself better. Like my daughter, I tell her, you don't play basketball against a kid that's terrible. You go out there and you play against a kid who's really good, and that's what's going to make you a better basketball player. So if we're comparing ourselves to everybody else who didn't do any work, who didn't put any forth effort, and we all pass, did we really pass knowing material? Or did we pass because we were just so bad that everybody was bad together? Do you get what I mean? Like, I don't understand why, I get that this should work, but I just think there's too many variables. I want a test that says, listen, if you know this material, then you are good enough to go on to Algebra 2 because you know your Algebra 1. I don't want to be compared to other people. I want to be compared to the content I need to know. So if I pass this test, I know everything I need to know from Algebra 1, and I can be successful in Algebra 2. That's how I think it should be graded. Not because Joe Schmo doesn't know anything, and I don't know anything, we get to move on together to Algebra 2. Right? Because Algebra 2 doesn't go, you know what? you and Joe don't know anything, so I'm going to calm down a little bit and I'm going to make it. No. And algebra 2, if you don't know how to factor, is it really hard to be successful? Does it matter that Joe doesn't know how to factor either? Do we get to go, hey, we both don't know it, so algebra 2 goes, you know what? We'll take factoring out. No, it can't happen. You guys get what I'm saying? So they've tried to, I believe, are trying to get rid of this because they're starting to realize, it's not the best way to compare. Now, what they're hoping is that statistically, there's enough students that the bell curve will work out. Because you have to remember, there's thousands, probably hundreds of thousands of students who are taking that test. So they're saying that our sample size should be big enough that I should get enough kids to where they fully understand. Does that make sense? Do we understand the bell curve? Okay? So it really doesn't, in my eyes, a bell curve just compares everything to everyone else. It doesn't really compare, like, doesn't tell you how much you need to know in order to move on. Does that make sense? Like everybody knew 40% of algebra 1. Awesome. So, if I went one more standard deviation, if I went out one more standard deviation, what do I know my percentage will be? 99.7% of my students will either have scored a 50 or an 80 on the test. Does that make sense? So that is what this bell curve is talking about. There used to be this thing that you guys did that was called a box and whisker. And it's kind of similar to that. Okay? This right here was the min. This right here was the max. This right here was the median. This right here was the, I believe that's the mean of the lower part. And this is the mean of the upper part. It's either the mean or the median. And you take it and you only do the numbers between here and here. And you only do the numbers between here and here. And that's how these numbers are made. You guys kind of remember that from the box and whisker? Okay? And remember, like I said, minimum value, that's the lowest. That's the lowest person who scored on the test. This would be the highest person who scored on the test. And up here they're saying that, oh, that's what it is. I think it's the median. I think it's the median for both. I think this is the median down here, and this is the median up here. So here's what happens. This is the median of the whole thing, correct? So I know when I do the median, I count my numbers. Right? And I start marking them off, and I find the middle number. Correct? So I know that 50% of my numbers are up here, and I know 50% of my numbers are down here. Make sense? And then I do the median for this part, and then I know that 50% of 50% is down here. Well, what's 50% of 50%? 25. You with me? So then I know this is 25% of the data, this is 25%, this is 25%, this is 25%. That's where these came from. So you do the median, and then you do the median of the lower, and you do the median of the upper. That's called a box and whisker. And the reason you can do that is then you know 25% of your data is here, 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 and there. Is that, yes? Makes sense on why it works? Yeah. All right? Isn't that similar to what we do, except ours has 68 for our, we get our, instead of a median, what do we use as our middle? The mean. And then we know that one standard deviation and one standard deviation above is going to be 68%, where the mean from the median to one median and the other median, how much percent of the data do we know is in there? 50%.
Okay, so
No. It's just another way of representing data.
okay, so you have
So the 10th on the problem asks you. This is of old. This is something that you probably did in probably pre-algebra. This is probably covered in pre-algebra. You did. It was all the like math 7 or 6th grade math. Okay, so you probably did this. Maybe you did a little bit in algebra, but that's called a box and whisker. Some people don't cover it because it's not used as much in my, like I haven't seen.
yeah. But I liked it. I remember understanding it pretty well.
Yeah.
That's what I was
All right. Now determine the percent and explain your reasoning. So right here it says what percent of the data is greater than the mean? Shouldn't be that hard. Think about it. Where is the mean located? So what does that mean? How much of it is going to be greater than the mean? 50%, right? And how much is going to be lower? And we already talked a little bit about this, right? Remember, this was 34 and this was 34. They're both mirror images of each other. So if they're going to be mirror, that means this has to be 50 and this has to be 50. So we slice that 50% up. Yes? You following me? Now, what percent of the data is between the mean and 2 standard deviations below? Okay, we did this already. We said how much was this total? It was 68. Yes? So how much did we say this was? Right, because they said what percent is 2 standard deviations below? So I need to go all the way out to here, and I want to know what is this percent right here that falls in those two categories. Are you following me? Well, I know that this whole thing from here to here is 68, so I know half of it is 34. Well, what did I say this whole thing was? We said it was 95, correct? And we said that means this is 27 added with this. That would account for 27%. Do we want 27%? We want half of 27, which is half of 27. What? So then we take 34% and do what? Add 13.5. And how much of the data is going to be there? Does everybody understand how we got that?
Yeah.
Following me. What's another way I could do this? Because we're breaking it up because we're going to have all these little percentages here in just a minute. But what's another way we could have just done that? Probably been quicker. How much does all of this account for? What did we say? 90, no, not 3, so that's 90, that's 3 standard. How much did we say? 95. So how much is this going to account for? From here to here. Half of 95, which half of 95 is 47.5. Half of 95. I counted this whole thing. Notice I did not include this. That's why it's not the full 50%. My little tail got cut off. Kind of like my doggy. Someone cut it. I didn't do it. Somebody else cut it. I don't know. We're trying to figure out why they cut his tail off.
Oh my god. I tried to bring a look outside the other day and I came back inside and his tail was still like a little before.
All right. I think we're getting this. I think this is awesome because this is going to be a huge part for everything else that we do is understanding this bell curve. What percent of data falls between 1 and 2 standard deviation? So, and this is above the mean. So I draw my curve. This is my mean. This is 1 standard deviation. This is 2 standard deviation. Correct? Okay. Correct? How much? Come on. How much did we just say this was worth? We just said it was 47.5, correct? We just did that problem. It was just down here. But if this is 47.5, then I know the other side has to be 47.5, correct? Now, I only want this part. You with me? So don't I know that this is 47.5? How much is this worth? We said it was 34%, correct? So what can I do to get what this value is? If this whole thing from here to here is 47.5, and this accounts for 34% of that, I can take 47.5 and minus 34, and that's when we're going to get the 13.5 that we already have. Are you following me where all these numbers are coming from? Out here we know that it's 2.5%. Again, how they did that is we just figured out that this whole thing was worth 47. Oh, what happens? 47.5, it's off now. So then that means if this whole thing, we said below the mean is how much? How much is from the mean and all the way below? What did we say it was? 50%. Gosh. Alright, so then we just took the 50 and minus the 47.5, and that's how they get that 2.5 is from 2 standard deviations below. You guys following me? Alright, come on. So a normal curve is, we're going to use the normal curve to answer all these questions. I will finish this video and put it up there. Please make sure you watch this. We got to be almost finished with this section. Alright, so we use the normal curve to answer these questions. Tell whether a distribution represents a population or a sample. So what percent of adult males have a height between 62 inches and 74 inches? And so right here, they give me this, and I know that this is 1 standard deviation, and I know that this is 2 standard deviations below. And so we figured out all those percentages. We know that this accounts for, we said this is 34%. We said this is 34%. And then this one we said was worth, this one was worth 13.5. And so when we add all those together, we get that it's 81.5% of the adults should fall between 2 standard deviations below and 1 standard deviation above. And since I know this is sigma, sigma represents that this is a population. So that's a population. Right here, we know that that means that that is a population, not a sample. When I go down here, again, this symbol means that is a population. And they said, what percent of adult females are taller than 68.5 inches? And I know that that's 1 standard deviation and above. And I know that this percent is worth that 13.5. This was worth that. Well, what they did is they said that this right here, they said from here over is 50%. And I know that this is 34%, so they took 50 and minus the 34, and then they got that it was approximately 16% of the females. And this is a population. because of the way that they wrote these things down here. This is the mean that tells me it's a mean of a population. That tells me that it's the standard deviation for a population. Right here, I know that this tells me that this is a sample, and that's the mean of the sample, and that's the mean, that's the standard deviation of a sample. That's why they use the S. So what percent of the scores were between here and here? Well, that's one standard deviation. That's just 34%. So that's it.